In the layered architecture of IoT systems, the perception layer is the one closest to the user. It is the layer where end devices operate. There are sensors, such as temperature, light intensity, humidity, and output devices, as well as actuators like bulbs, radiator controllers, and shutters. All such devices use some kind of computer, usually not visible to the user, with limited computational power. Such a constrained computer is similar to the embedded system, which we can find in modern home appliances, e.g. washing machines, but with one significant difference. It has a communication unit built in. We can present the IoT end device as the computer built with four functional modules: sensing unit, processing unit, communication unit, and power supply unit, as in the figure. The processing unit is an essential part of every computer. It consists of the microprocessor, memory for the program and for data, and peripheral devices, all connected together with address, data, and control buses. In modern embedded systems architectures, the mentioned elements are often integrated into one chip, forming the single chip computer, also called microcontroller or embedded processor. If such an integrated circuit contains additional expansion modules, like a radio module, it is called a system on chip. Other possibilities are digital signal processors, especially in the systems implement some audio and video processing, application-specific integrated circuits, including application-specific processors designed for specialized use, popular in high-volume device production. Field programmable gate array, which allows us for flexible reconfiguration of the hardware, enabling the implementation of different microprocessors with other elements of the whole device in one universal programmable and configurable integrated circuit. Nowadays, microcontrollers or systems on chip are a prevalent choice for building IoT nodes. A typical microcontroller includes a set of general-purpose units: CPU core, program memory, data memory, timers, counters, interrupt controller, I/O ports, serial synchronous and asynchronous communication ports, analog to digital converter, pulse width modulation unit used for digital to analog conversion, DMA controller, supervisory units like watchdog timer, reset circuit, brownout voltage detector. Embedded processor or system on chip can also contain network interface, USB controller, memory interface module, floating point unit, cryptographic module, and other application-specific extensions. The CPU core is the brain of the microcontroller, responsible for executing the main program. It manages program flow, executes instructions, calculates addresses, and processes integer values. Program instructions are fetched from program memory, which is usually implemented as internal or external flash memory. Data is stored in internal data memory, typically static RAM. If more memory is required, some microcontrollers have a memory management unit that can connect to external DRAM memory. Flash memory often serves as a storage space for files. Timers and counters are essential units that generate precise pulses and square signals of selected frequencies. They measure delays, synchronize other modules like serial ports, converters, and displays, and can produce pulse width modulation signals to control motor speeds and light brightness. Microcontrollers are equipped with digital input and output ports, allowing connection to various system components. External sensors can be connected to gather environmental information, while output devices can manipulate environmental parameters. Analog inputs read voltage values from simple sensors, and serial communication ports connect more complex sensors and displays for user interaction or communication with other computer systems. The interrupt controller is a unit that automatically handles tasks specific to hardware events. If the interrupt is signaled, the appropriate subroutine is started, freeing the processor from constantly checking for device needs. This enhances the code's efficiency and reliability. Supervisory units help recover from abnormal situations. For instance, the watchdog resets the processor if the software hangs, and the brownout detector monitors the power supply voltage to prevent errors due to low voltage. Advanced units help to accelerate program execution and improve the efficiency of the system. The Direct Memory Access Module performs memory operations independently of the processor, efficiently copying data between memory and peripheral units. For rapid floating point calculations, a built-in FPU coprocessor handles real numbers and advanced mathematical functions. The USB controller handles complex communication protocols, while the networking unit performs wired or wireless data transmission. Other application-specific units free the main processor from executing software by moving tasks to hardware, which is faster and more efficient. In this course, you will learn details of the operation of many internal modules of microcontrollers, embedded processors, and system-on-chips.